Centuries ago, humans looked at the physical world and asked what it was made of. The answer seemed just around the corner. Zoom in on any object far enough, and surely you would find its final building blocks. Philosophers called them atoms, indivisible units, the irreducible substrate of everything. For a long time, that story held. Then, the 20th century arrived and smashed it to pieces. Literally, particle accelerators revealed that atoms were not the end of the line. Inside every atom was a nucleus, and inside every nucleus were protons and neutrons, and those in turn housed quarks. What emerged from this cascade of discoveries was the standard model of particle physics, a framework built on quantum field theory that describes the interactions of dozens of elementary particles. Its predictive power borders on the absurd. Quantum electrodynamics, the piece of the standard model governing how light and matter interact, has produced theoretical predictions that match experiments to better than 1 part in a trillion. Recent work at the Max-Planck-Institut for Kernphysik in Heidelberg measured the magnetic properties of a single electron bound to a hydrogen-like tin ion, and found agreement with theory to more than 10 decimal places. No engineering blueprint in human history has ever been this accurate. There is a deeply counterintuitive truth lurking at the heart of physics. Looking at something is never a passive act. To observe any object, you must bounce something off it, usually photons, the particles of light. At human scales, this barely matters. But when the object you are trying to examine is itself the size of a subatomic particle, the situation is catastrophically different. The probes you need to see such small targets must have extremely short wavelengths, and shorter wavelengths mean higher energy. That energy, on impact, inevitably disturbs the very thing you are trying to measure. This is the physical reality behind the Heisenberg uncertainty principle, introduced in 1927. It is not a limitation of instruments or a temporary engineering problem waiting for a clever solution. It is a structural feature of nature itself. Certain pairs of properties, position and momentum, energy and time, cannot both be known with unlimited precision simultaneously. The more you pin down one, the more the other blurs. For decades, physicists worked within these constraints, treating them as hard walls. Yet in September 2025, a team at the University of Sydney published research demonstrating a remarkable loophole. Rather than breaking the principle, they reshaped it, pushing unavoidable quantum uncertainty into regions of measurement that do not affect the desired precision. Think of it as squeezing air inside a balloon. You cannot remove the air, but you can move it out of the way. Faced with particles too small to ever directly observe, physicists did what creative problem solvers always do. They invented a useful fiction. They decided to pretend that each elementary particle is simply a point in space, a perfectly dimensionless location tagged with a few numbers like mass and electric charge. This is not claimed to be literally true. No one genuinely believes that an electron is a geometric point with 0 size. But by treating it as one, physicists could write down equations that were both solvable and extraordinarily predictive. The story of the point particle became the foundation of quantum field theory, and on top of that foundation, the entire standard model was constructed. Every particle collision studied at facilities like CERN, every precision measurement of atomic spectra, every calculation of how light scatters off electrons, all of it has been filtered through this convenient mathematical fiction, and all of it has worked. There is a profound philosophical lesson here that reaches well beyond physics. Scientific models are not photographs of reality. They are maps. And like all maps, they are simplified, stylized, and always somewhat wrong. The question is never whether a map is perfectly accurate. It is whether the map reliably guides you to where you need to go. For nearly a century, the point-particle map has guided physicists to some of the most precise destinations ever charted in the history of human knowledge. If quantum field theory were the whole story, physics would be in fine shape. It is not. there remains one fundamental force that stubbornly refuses to fit inside the quantum framework: gravity. According to Einstein's general theory of relativity, gravity is not a force in the traditional sense at all. Every other fundamental force, electromagnetism, the strong nuclear force, the weak nuclear force, is mediated by particles. Gravity, by contrast, is the geometry of space-time itself. It is not actors pushing and pulling on each other. It is the shape of the stage on which all actors move. And describing the geometry of space-time requires absolute precision about distances, the kind of precision that quantum mechanics, with its built-in uncertainty, cannot provide. Attempts to reconcile these two frameworks by inventing a quantum particle of gravity, called the graviton, have consistently produced mathematical nonsense. The calculations generate infinities that no known technique can tame. This collision between general relativity and quantum mechanics is not a minor technical issue. It is the central unresolved crisis of modern physics. Bridging it would yield what physicists call a theory of everything, a single coherent framework describing every force and particle in the universe. In the late 1960s and through the 1970s, a radical idea emerged. What if the point-particle map was simply too simple? What if elementary particles were not zero-dimensional dots but one-dimensional vibrating strings? Different vibrational modes of the same fundamental string would produce different particles, much as a single violin string can produce many notes. Most remarkably, when physicists worked through the mathematics, one mode of string vibration corresponded to a particle with exactly the properties expected of a graviton. For the first time, gravity appeared to arise naturally from the same framework as quantum mechanics. String theory seemed to promise a theory of everything. The complications arrived quickly. String theory works mathematically only when space-time has 10 dimensions, 6 more than the 4 we experience. No prediction unique to string theory has yet been confirmed by experiment. But in December 2024, researchers at NYU and Caltech published work showing that string theory may be mathematically inevitable, the only consistent answer to a specific set of constraints on quantum gravity. Meanwhile, machine learning algorithms are now being used to explore the near-infinite landscape of possible string geometries, with early results calculating particle masses from specific 6-dimensional shapes for the first time. String theory has also provided tools that illuminate the black hole information paradox, whether information that falls into a black hole is truly destroyed or secretly preserved in the radiation it emits. In 2025, physicists concluded there is now considerable evidence that information does escape, consistent with string theory's predictions. Whether or not strings ever become provably true, they are already extraordinarily useful. A story that, like all great scientific stories, keeps pointing toward truths we have not yet fully seen. Thanks for watching. If you have anything to add, drop a comment below. Don't forget to like and subscribe for more videos exploring the world around us.